In my presentation, I want to briefly talk about the random walk and use some practical applications or problems to induce the recurrent property and the transient property of random walk. The random walk is known as a discrete time stochastic process which describes a path consisting of a number of random steps and a mathematical space. It can be Rd or Zd, which d is a dimension. Uh, it has many practical applications in many fields, such as biology or physics or even the finance. The Brownian motion is a continuous analog of two-dimensional random walk, and there is a very close and deep connections between Brownian motion and random walk. Here is a picture of the one-dimensional random walk. Um, Let me give a definition of random walk. For x, which is random variables enter a mathematical space, we denote Sn as a random sequence, which Sn is equal to Sn minus 1, which is the previous term plus the Xn. And we also can write Sn as the z plus x1 plus 2xn. Where z is equal to s0, which means this is a original point. So for a simple random walk, for the z we just mentioned, we can denote it as 0 for the original point. And for each step, we only consider it either backward uh, or get forward with a distance of 1. So it can be written as -1 or +1. So for a simple symmetric random walk, which is a point we need to focus on today's presentation, it has the same probability for each choice. So for the one dimension, you can see for each xn, it has the same probability, which is 1/2. So there, we need to talk about the drunk people problem. So consider a drunk people randomly walk along a street, which means he walk along a line. Where we can consider this is a one-dimensional symmetric simple random walk. So the question is, what is the possibility for him to come back to the origin? So we can assume the steps he works Sn and the distance he works for is Sn. From this formula, we call that the Pascal triangle. We can see these things means the possibilities, and here the column denote as the steps he works, and the row denote as the distance he works. So we know when the steps n is equal to a odd number, as you see for 1, for 3 here, the possibility for going back to the original point is always 0. So only if n is a even number, which we denote n is equal to 2k, we want to find the possibility for backing the original point. So we assume the capitalized n is the number of paths to the origin. So we know for each number of paths, the possibility to back to the origin is a number of paths divide the total paths, which is 2 to the power of n. We can write as this binomial coefficient form. Using the Stirling formula is a very good approximation for the factorials. So for this possibility, we can further write it as this form. Since n is equal to 2k, so we can write as n factorials divide k's factorials times k's factorials. So using the Stirling formula here, we can get a little bit long expression. So where the 1 times epsilon epsilon is a very small number. As n go to infinity, epsilon n or epsilon k will eventually go to 0. So after simplify, we can get the formula of this. And our goal is to calculate the sum of the possibility to say if it will goes to a infinity, the sum, or it will converge to a certain number, to a certain constant. So as we see, if n goes to infinity, k also goes to infinity. So as both goes to infinity, the 1 plus epsilon n and also 1 plus epsilon k will, they both go to, like, this term will go to 1, right? Because epsilon will go to 0. So we only get this sum. Using the knowledge we have already learned in Math 2B, using the p-series test, this square root of pi is a constant, and we see the one half is less than 1, so this is actually diverge, which means it goes to infinity. So we can know the sum goes to infinity eventually. This means the random walk is recurrent, and the drink people can find their way for infinite times if they, as long as they walk around. For the two-dimensional, we have the 4 choice for each step. So if we assume there are 2n steps, the total path will be to the power of 2n. As the same process, we can assume the total path be capitalized n, and as you see here, the step for going back, uh, or going forward should be equal, and going left to going right should also be equal. So we assume going left is k, right also be k, and the step going up will be n minus k, and going down will be n minus k as well. So we get the formula of the capitalized n. Then we know the possibility for each number of paths. We can write it as this form, and you should know this binomial coefficient is equal to 2n, like this form. And we can, using the Stirling formula, to get a approximation for this, for the p. After simplify, we can get the pi times n over 1. So the sum, as n goes to infinity, as the steps go to infinity, we can know the pi over 1 is only a constant, and see the n over 1 is we're using harmonic series test, and it also shows a diverge. So we can get the same conclusion for the two dimension, which is also divergent, and which means the people will eventually go to their home as long as they walk around. How about the higher dimension? So we assume a drink bird, flies through a 3 dimension. So it has actually six choice for each step. So this means for 2n steps, the total path will be 6 to the power of 2n. The calculated steps are similar as the previous proof, but this actually will be very complicated for the calculation because we have 6 directions, and the variant will be like 2 or 3. It depends on which you assume. So according to the Stirling formula and a series of complicated calculation, we eventually get the result, which is the sum of the possibility is by comparison, we get the sum of possibility is equal or less than a constant. This is a constant term times a sum of this term, and we use the p-series test. as this term is greater than 1, right? So it will eventually converge rather than diverge. So we derive a different conclusion. So we know the 3-dimension is diverge, and which means that a drink word cannot infinitely come back to the origin. At a certain time, it never comes back anymore. In this slide, we use basically on using some probabilistic calculation, covert analysis, and binomial approximation with applying the Stirling formula to analyze recurrent and transient properties for the symmetric simple random walk. Thank you for listening my presentation. Thank you.